Hello, and welcome to Cerebras Systems Customer Spotlight at Supercomputing 2021. I'm Rebecca Lewington, and I'm very pleased to be joined by Dr. Venkatram Vishwanath, who leads the data science team at the Argonne Leadership Computing Facility. I'm also joined by Cerebras Director of Product, Rebecca Lewington. We're here to talk about the Argonne AI Testbed, which aims to evaluate the usability and performance of machine learning-based high-performance computing applications running on next-generation AI accelerator machines. Thanks very much to both of you for joining me.
Thanks for having us.
Thank you for having me. Thanks for having us.
It's my pleasure. So first, Venkat, could you tell us about the Argonne Leadership Computing Facility and the kind of research that you support?
So the Argonne Leadership Computing Facility is a Department of Energy, Office of Science user facility where we work with users to do open science research on some of the largest supercomputing resources available to the community. So think about access to the largest systems to do open science research, to run campaigns and science models spanning better understanding, say, cosmology, design of solar cell batteries and materials, understanding operations of tokamak reactors, personalized medicine, among others, a wide variety of fields where you need extreme amount of computing. We have these users who come on our systems, apply for time and allocations to do really challenging science problems that's not possible on any traditional clusters that's in their universities or at other places.
Excellent. This is big science.
Exactly. This is big science.
Wow, that's amazing. So Jessica, same question for you. What's your background and what's your role at Cerebras?
Yeah, so I'm one of our directors of product here at Cerebras. And as a director of product, I work at the intersection of our users and our engineering team to make sure that we're building the right types of AI compute solutions for our users. And as part of that, I'm lucky enough to work directly with some of our closest collaborators, like Venkat at Argonne National Labs.
Excellent. So Venkat, can you tell us what you're working on right now, and why you're working on that, and what you hope the impact will be if it works?
Let me start off with one of the projects that that's very near and dear to me, and which has been an excellent collaboration with Cerebras and with Jessica and Andy and their entire team at Cerebras, where the goal is to better understand protein-protein interactions, and in this specific case, to understand how the SARS-CoV-2 spike protein interacts with the human host cell. And as you know, in this time and day, it's very important for us to understand these interactions so that it can help us with novel drug therapeutics, understanding various mutations, among others. So this is a multidisciplinary project where it brings together computer scientists, applied mathematicians, biophysicists, folks with really expertise in large-scale simulations, together with expertise in AI. So it's a group which has come together to solve this really exciting problem. And I would say I'm happy to say that we are one of the Gordon Bell finalists for the COVID-19 at supercomputing this year. And in this case, our real goal is to understand, can we accelerate understanding these protein-protein interactions and to better understand the drug design space? So, traditionally what we do is we run really large ensembles of simulations where to understand these interactions, we're talking about the size of atoms that we want to simulate over here in the range of maybe 1 million atoms, I would say today. The systems that we really want to understand going forward are in the billion plus case. So at the million atom simulations, given all the possible interactions, we want to really see if we can quickly sample and identify candidates of interest. So the way that we would have done in the past is run a large ensemble of simulations. We would let them evolve and see what might be interesting simulations. And if there were configurations that didn't yield any results, we would start new ones. Well, we could do it better. So here's where we could steer these simulations and the search of the space using AI. So we've been working with the Cerebras and with Jessica and her team, where we've used a variational autoencoder where we let the simulations evolve. We use this data to really train a large model on both the CS1 as well as now on the CS2, and help us sample this space, actually build a latent representation in a lower dimension and see if we can efficiently sample the space. This helps us understand simulations that have been yielding us effective results, continuing them on, simulations or the space that have already been sampled well, so we can stop them, and we can spend the compute cycles onto other spaces or in the search space where we haven't spent enough time searching or understanding the search space here, so we can put our time and effort in understanding interactions in that space. So think about this as an intelligent sampling of this entire space, which basically has yielded us a 50x improvement over just running an equilibrium ensemble simulation. So this yields us at least 50x improvement in time to solution, which is, I would say, a great step forward in design of novel therapeutics. And what we have done in this space is we have coupled traditional simulations, which are good for running molecular dynamic simulation, together with the Cerebras CS-2 system and the CS1 earlier, where we could run the AI for both the training as well as for inference that will help us, steer the simulations in the right space.
Can I ask you something about that?
Go ahead.
What's the role of the training the model versus the role of using the model for inference in this particular case? Could you say a bit more about that?
Oh, definitely. So the goal for training the model is to build this latent space. And we are using this model. It's a variational autoencoder. So based on the protein interaction trajectories that we have, we use that information to build this overall representation of the space. And when we apply it in an inference mode, we use this train model to get the current trajectories from the interactions to tell us information about, either what might be an outlier, or where in the space are these trajectories mapping onto in terms of a clustering, if you want to look at it that way. So it tells us information in an inference mode about what have we seen, or what should we be, perhaps trying to apply more compute or identifying outliers in the space based on the trajectories. So it gives us insights on the ongoing simulation and how these trajectories are evolving over time in an inference mode.
Got it. Thank you. What else? What else are you working on?
Oh, again, this is just one problem one interesting science problem that we are working on. Talking about the cancer space, we are looking at drug response for various tumors. That's another problem that we have. We have projects where we are looking to better understand the connectomics, which is the human brain. So we work with scientists at the University of Chicago together with Princeton and Harvard University, where we work on electron microscopy images that we can obtain. So in this case, we are looking at, say, a mouse brain, where at a nanometer scale resolution, where you section these together. And one of the big innovations designed by Bobby Kasturi, who's at University of Chicago, is on an automated way to create an end-to-end pipeline for this. So you can section these off. It gets imaged, and you can then build a pipeline where you can reconstruct them. In this case, so each image in this case is in a nanometer scale resolution, and you can get it approximately 80K by 40K pixels, which is really just one small image of this entire volume. And the goal over here is to look at, can you reconstruct the neuroanatomy of a mouse brain? Where we want to go is to target human brain, which is, mouse brain is about 1 millimeter cube, and human brain is, I would say, a factor of magnitude in each of the 3 dimensions. So you're talking about at least 1,000x increase in both the scale of the data in this case and the resolution. So the key thing that we want to understand in this case is, can it help us understand Alzheimer's? Can it help us understand better materials which are bio-inspired? Can it help us understand better computing as well? So you have interesting questions that you want to answer from both from a therapeutics point of view, from a computing point of view, and the scale of the data sets that we are obtaining and will obtain requires computing at an extreme scale. And the models here are also much larger.
It seems like there's an interesting theme here that you're preparing to do things that are much bigger again. Like if you're trying to do a mouse brain that's this big and you want to go 1,000 times bigger, I'm guessing you're not finding it very easy to model the entire mouse brain yet. So what are some of the bottlenecks going forward for this kind of work? And how can Cerebras help?
Oh, indeed. So, so one of the key things that we're working as part of the AI testbed and with Cerebras is to really understand how will AI accelerators play a key role in design of future supercomputers. If you look at the way supercomputing has come, it's taken us at least, I would say, a significant portion of the time to make GPUs an integral part of computing for, at least for scientific computing. And, given the performance that we are seeing on, systems such as Cerebras, the key question for us is to understand, how do we architect future systems so that we can build it at a scale where we can start solving, some of these really challenging problems. So an open question that we are working towards, and Jessica and her team are very closely involved in this, is really trying to understand, do we build disaggregated systems? So we have racks of compute, which are tightly linked with racks of AI accelerators such as Cerebras. How do we design the software stack? In case these are co-located on the same node, how do we design a software stack where we can even do HPC style workloads on the Cerebras chip? To your questions about bottlenecks, tackling compute, which is very relevant for scientific machine learning, which spans a wide range of applications. That's one. Being able to deal with scientific data sets, which are very different from perhaps what you might see in the commercial space, is another dimension to this problem that we need to tackle here.
So you've got many types of decision you can make regarding system architecture and regarding software architecture and all of these things all at once. So testbed is, I guess, the place to do that.
Indeed.
Jessica, what about the Cerebras architecture makes us able to help here?
Yeah, I think to understand this better is also helpful to talk a little bit about the problem that we're trying to solve. And I think that this is a perfect case of a specialized solution for a specialized problem. And if you think about what a neural network is from a computational perspective, if you just Google image search for it and see what they look like, what you see is often these very large linear algebra compute graphs where you have nodes that are trying to talk to each other from layer to layer, and there's a massive amount of communication between the layers. So you have this problem that's extremely compute heavy, especially for some of these modern neural networks like the variational autoencoder that Venkat talked about. So you need a huge amount of compute, but you also need a huge amount of memory and a very large amount of communication. So this is not really your typical general compute problem. Now, what we're often doing today as an industry is we are taking this interconnected, very large problem and trying to distribute it across an extremely large cluster of traditional small processors like CPUs or GPUs. And what you often have to do in that case is scale to tens, hundreds, and in Argonne's case, sometimes even thousands of these small compute devices, which is possible, but which is not always efficient. And where you see that there end up being a lot of bottlenecks in memory bandwidth, and in particular in communication bandwidth when you're trying to do this massive all-to-all communication in the neural network. So what we did at Cerebras is look at this problem, recognize that there is a lot of inefficiency in having a general compute architecture for a specialized problem and this large scale-out complexity. And what we did is design a new type of chip specifically for AI compute. So that means that our architecture has been optimized for the sparse linear algebra graph computations of the neural network. And then what we did on top of that is, frankly, we made an extremely enormous chip. So we took all of this and we made a giant chip that's about 56 times larger than the second largest chip in the world, makes it about the size of a large dinner plate, or maybe more relevantly, the size of a full silicon wafer. And what that allowed us to do is pack 850,000 of these AI optimized cores all on a single piece of silicon. And if you can imagine, just the type of communication bandwidth that you can get when all of these cores are connected via silicon is just orders of magnitude larger than what you could ever get when you have all of these small nodes communicating across wires and across different servers. So that's really where a lot of our advantage comes from. When you're looking at these extremely computationally expensive and communication expensive neural networks, the Cerebras solution essentially provides the computational power of an entire cluster of traditional compute units, but within a single system on a single chip, with all of the efficiencies that come from that from a compute and power and also complexity perspective, and makes it also much easier to program. And with our solution, we've been able to see with collaborators like Argonne that we're often able to show 50 to several hundred times acceleration over traditional smaller processors.
Right, and there's not just the fact that you've got a cluster's worth of compute on one wafer, it also means that the software is simpler, right?
Yeah, exactly. So I think Venkat can speak better to this as a user of these clusters, but typically distributed computing is itself an entire field of software research. It can be very complicated to figure out how you deal with synchronization issues, to deal with communication issues, when you're trying to take this larger problem and figure out how to distribute it, not only data parallel across multiple devices, but also model parallel, which means you're trying to cut up the neural network itself into smaller pieces across many small devices. And on the Cerebras system, because we're such a large single node, what it means is that for most networks, you can actually fit the entire neural network on a single Cerebras chip. And in cases where the model itself gets really large, we can go one layer at a time. And even then, a single layer can be an enormous size of about 100,000 by 100,000 matrix size. And so you never really have to get into this model parallelism complexity that you typically have to think about when distributing across a very large cluster. Instead, your research scientists can access this cluster scale acceleration, but with the simplicity and ease of programming a single node.
So, Venkat, how do you incorporate the Cerebras system into your existing supercomputers?
That's that's one of the key innovations that we've had to work on how do you really couple heterogeneous systems together to solve challenging science problems as part of a workflow. So we have a rich ecosystem of traditional simulations, and what we are moving towards, at least in the space, is coupling AI together with simulations to either build surrogate models, to build where we could accelerate portions of a simulation, or we could build steer simulations, or even in some cases you could and where you don't have sufficient models, you could build a model out using data that you acquired, building AI models, and then coupling these models together to really be part of a simulation. A key driving factor is, where do you run the right compute at the right place, and how do you couple them together as part of the entire ecosystem to make it work? So something that we've been able to work very closely with Cerebras is working to facilitate workflows. So we have, in this case, as part of the COVID-19 2021 Garden Bell Run, we have Balsam, a workflow that we have developed to help us launch workflows cross sites. So we could run it at multiple sites, and where we could couple, say, a simulation running on in this case, a system running at NERSC on Perlmutter, together with a simulation running at Argonne, with the training and inference running on a CS-2, all together to really solve these problems in real time.
Could you tell us a bit more about the purpose of the AI Testbed at the Argonne Leadership Computing Facility? What are the goals for that project?
Some of our key goals is to really understand, the design of future supercomputers to really enable productive AI for science at scale. And as we work towards it, working with various vendors to understand what are the system architectures that should be part of these supercomputers, as well as the software stack to enable productive science on these systems.
Got it. It's not a small thing, is it? Because Aurora is an exascale machine. Will it be the biggest, hopefully, machine, or at least the biggest useful machine in the world when it's done? So you're thinking about what's coming next. So that's amazing. Jessica, what's this collaboration with Argonne been like for you and for Cerebras? Because ANL is a bit of a special case, isn't it, for us?
It is, and it's actually been extremely fantastic and collaborative for us, and we've learned so much from this collaboration. The team members at Argonne were actually our very first users back when we shipped our very first Cerebras system, and I think version 0.1 of our software. And so we've gotten so much feedback, so many ideas that have been exchanged. I actually got some feedback this morning that we need to improve our documentation on our input pipeline optimization to include some examples. And I think that's exactly what we want. And I really think that's the best way to build product, is to have these really tight collaborations with our users. And the Argonne team in particular, since they're always on the cutting edge, is always pushing us to develop new features, to develop more generic features for our architecture, and to think about use cases that we otherwise oftentimes had not even considered for ourselves. So as an example, I think just a couple of months ago, one of the teams at Argonne was working on accelerating a very small neural network. And this is the problem they came to us with. And I think it wasn't something we typically even ourselves thought would be well suited to our large chip architecture. But in our collaboration, what we figured out is that we could actually build this mechanism to take a very small neural network and replicate it multiple times across the entire surface of the fabric and train that model in a data parallel fashion. And what we saw was that it was actually extremely efficient, because in this style of data parallel training, where all the communication was done on silicon, it was much faster than what they were even able to see when they were working on a large cluster of other devices. And I think on that, we were able to see several tens to hundreds. In this case, I think several 100x improvement over what the team was using previously. So I think that's just the type of thing that we've been able to learn in our collaboration with Argonne. And now that's one capability we're taking to production. And we've already done that for dozens of other features.
Brilliant. So Venkat, you've got another two more systems coming from us, the CS-2 systems, the new ones. What are you hoping all this is going to unlock for you next?
Well, it's going to definitely unlock more science for us. That's the key goal for us. And some of the problems that we have more data that we're acquiring at higher resolution. So we're really excited that CS2 will be able to help us tackle, interesting scientific machine learning in a wide variety of domain at larger scales. We're already working and As you've seen, we are getting exciting results with in several application areas, and a larger CS2 system will only unlock more of these scientific discoveries. So this is really exciting. And like I said earlier, in the case of the SARS-CoV-2, we are looking at the 10 million atom case today. Where we really want to go is the 1 billion atom plus simulations. So in some cases, going from, if you take the variational autoencoder, you're looking at it, we are converting the trajectories into contract matrices, which are, 1K by 1K. And we have 6K by 6K. So our goal is, this is an immediate problem for us to solve today. That's one. Another, again, I talked about the connectomics, which is going to be, to solve the connectomics problem, some rough estimates say that it needs us to run 3 years of dedicated compute on Aurora at an exascale, scale to tackle the human brain. So that might be, another way to see using the technologies that is there today. So that's based on today's GPU accelerated systems, that's estimate. But taking that and running on the Cerebras system, if we can get a full magnitudes of improvement, that will really yield significant insights. We have ongoing work in natural language processing to mine scientific literature. That's another direction that we have active work in. So I'm really excited that the 2-rack system is going to unlock a lot more science for us than what we have. And again, working closely with Jessica and her team, which has been, a very good close collaboration where we can provide them feedback. They can, they provide us guidance on how we can better tune our application code to fully exploit the Cerebra wafer scale engine. Has been really, we've learned a lot from this collaboration as well, and it's been a good partnership.
Well, and long may it continue. So, since you spend much of your time thinking about what's coming next and what's coming beyond that, it's like to finish off with a blue sky question. What would you do if you had unlimited compute resources?
Oh, great question. We have, we are just scratching I would say, the tip of the iceberg here. We have really interesting and challenging problems ranging from climate, design of more efficient organic materials for, say, solar energy, improved operations of various nuclear reactors, fusion reactors, cybersecurity, which needs tremendous more compute than what we have today. Personalized medicine at a population scale is another really interesting problem that we'll be looking at, Connectomics, among others. So trying to tackle these problems is what keeps us going and what keeps me up every day, and working on these interesting problems. So the more compute that we can have to solve these, our next problem challenge beyond that would be interconnecting them, because they all are very much an interconnected problem at the end of the day. So there is a lot more that we can solve as a global community here. So
this is all terribly exciting, and thank you so much for joining me, both of you. It's been a very interesting and inspirational talk. I hope everyone enjoys it as much as I did. Thank you.